Okay, let's unpack this. Every day, it feels like we get hit with this tidal wave of AI news.
It's constant.
Yeah, a new model, bigger parameters, faster inference, better benchmark scores.
Mm.
And for you, the listener, the technical decision maker, maybe the product manager trying to build a new system, it's, well, it's not just noise. It's a real strategic challenge trying to figure out where to put your resources, where to focus.
It absolutely is overwhelming. And, the set of sources you've pulled together here, they really cut right to the core engineering choices people are facing today.
Mhm.
We seem to be moving past just the headlines, the ones celebrating raw model size, and diving more into the strategic roadmap. How do you actually implement this stuff effectively? We need to define efficiency, not just like raw capability.
That's exactly right. We've got research here covering the fundamental trade-offs in large language model selection, LLMs, focusing really intensely on that implementation strategy, model efficiency, and also some deep dives into these advanced architectures like AI agents and uh, fascinatingly complex mixture of experts, or MOE.
Yeah, and what's truly fascinating, I think, is that the central question is shifting. It isn't just which model is the undisputed best, full stop, anymore. It's more like which model is right for this specific job, right here, right now, in this part of the data pipeline.
Okay.
So our mission today really is to distill that strategic decision matrix. We need to get people thinking beyond a single model mindset, the old LLM or nothing, towards more of an ensemble strategy. How do you maximize the overall business value through cost-conscious dynamic efficiency?
Precisely. And to do that, we first have to understand that fundamental tension. When do you go large? When do you go small? And crucially, how are these cutting-edge architectures making those smaller models surprisingly powerful? Powerful enough, maybe, to meet most of your needs. Let's start with the basics, the foundational strategy,
hmm
the size-performance trade-off.
Okay, so to ground this discussion, we first have to properly define what size even means when we talk about an LLM. When we talk model size, we're measuring the parameter count.
And these parameters, they're not just arbitrary numbers, right? They are the floating point weights, literally the individual numbers that the neural network adjusts, through constant iteration during training.
hmm
You could almost think of them as the neural network's memory slots and its skill set combined. Collectively, these hundreds of billions, sometimes trillions of weights, they encode the model's entire knowledge, its grasp of language, its ability to reason.
And the scale across the market is just immense, which creates huge strategic differences. We are talking models running entirely on a standard smartphone, maybe only 300 million parameters, like in the hundreds of millions,
Wow.
all the way up to these massive frontier models like, say, Llama 3 400B, that needs dedicated racks of high-end GPUs just to operate and clocks in around 400 billion parameters.
Yeah, that puts the scale into perspective instantly. We're
Uh,
talking maybe a highly efficient model like Mistral 7B, 7 billion parameters,
Yeah,
versus that 400 billion parameter beast.
exactly.
But the critical decision, the one that really defines your operational budget and your latency, is that central compromise,
Yeah.
performance versus computational cost.
That's the absolute core of the strategy. The whole decision hinges entirely on the trade-offs you make when you scale up. If you go big, you get clear, measurable advantages.
Like what?
Well, substantially more memory for factual knowledge, better support for a wider array of languages, and the ability to execute much more complex chains of thought, multi-step reasoning. These bigger models are simply better at handling ambiguity and complexity.
Okay, but the downside is where the practical engineering choices get, well, painful, right? Scaling up introduces exponentially higher compute requirements.
Conventionally.
And that translates directly into greater energy consumption, significantly larger memory needs, which impacts your hardware choices. This cost explosion affects both the initial training and, crucially, the ongoing inference, the production operation costs.
Yeah, that inference cost is often the killer.
So bigger might often be better for raw, generalized performance, but it is almost never better for your long-term balance sheet or your internal sustainability metrics, for that matter.
This is precisely why that strategic rule of thumb we found in the sources is so valuable. You must align the model size directly with the complexity and the scope of the task at hand.
Right tool for the job.
Exactly. And often that tool isn't the biggest, most expensive one you can find.
So when do you absolutely need the giant model? The sources say you reach for the large models when you require that expansive open-ended reasoning or tasks that demand a broad, deep, generalized knowledge base. The sweet spot is complexity and context.
Think complex multi-file code generation. Maybe something spanning dozens of ecosystems or document-intensive work across vast, sometimes unknown or highly specialized contexts.
Okay, like broadband code generation.
Yeah, take that example. A smaller model might handle basic Python scripts fine, but a frontier model could potentially cover dozens of languages, reason over complex edge cases, maybe involving deprecated libraries, and work with unknown APIs across huge projects simultaneously.
Right.
These models are necessary when the surface area of potential knowledge required is just enormous.
And we can't overlook the importance of document-intensive work either. The sheer length of the context windows that these large models support is critical there.
Absolutely.
Processing legal contracts, specialized medical guidelines, massive technical standards. It requires the model to hold vast amounts of information in its immediate working memory.
And that capacity directly reduces hallucination rates. It drastically improves citation quality, which is, well, paramount in regulated industries where accuracy and being able to verify the source are non-negotiable.
Okay, so that's the case for large. Conversely, the small models are strategically positioned for more focused capabilities.
Exactly. If your goal is a specific task, like text classification, maybe straightforward Q&A against a known dataset, or just routine summarization, a small, carefully fine-tuned model can often deliver, say, 90% of the quality of its larger counterpart.
And the kicker.
The kicker is it does this at a tiny fraction of the operational cost and with vastly superior speed, lower latency.
Let's dig into those specific use cases for efficiency, because that's where the business case really shines, I think. On-device AI is maybe the most obvious example.
For sure. If you need extremely low latency, we're talking under 100 milliseconds, and strict privacy, like for local keyboard prediction or offline search, maybe real-time gaming assistance, the model has to run locally on consumer hardware.
Which means it has to be small.
It must be small and highly optimized, no way around it.
But the truly disruptive business case, the one highlighted in the material, is an operational efficiency for just everyday tasks, like routine summarization.
Yeah, that was a fantastic sweet spot example. There was a specialized study showing summaries generated by Mistral 7B, that 7 billion parameter model, were statistically indistinguishable in quality from those created by the much larger GPT 3.5 Turbo.
Indistinguishable, really.
Statistically, yeah.
Yeah.
Yet Mistral 7B ran 30 times cheaper and significantly faster in production environments.
30 times cheaper. If you're processing millions of customer feedback forms or daily reports, that 30x saving translates directly into massive operational ROI and a smaller hardware footprint.
Huge savings. And for focused enterprise applications, the value of fine-tuning really can't be overstated. IBM found that when they fine-tuned their Granite 13B model family on specific enterprise handbooks for Q&A tasks,
Oh,
that specialized 13B model matched the performance of generalized models 5 times larger for those specific questions.
wow. So you're getting bespoke, high-quality performance precisely where you need it without the astronomical inference costs you'd get deploying a generalist frontier model for everything.
Exactly. And this efficiency leap is driving one of the most exciting trends we see in the data. Smaller models are getting smarter, faster.
Right, the compression of competence.
You can track this really clearly through benchmarks like MMLU, the Massive Multitask Language Understanding Test. It objectively measures knowledge across really challenging domains like math, law, medicine.
Okay, and just to set the baseline for our listener, random guessing on MLU is like 25%, right? Average competent human scores maybe 35%.
Around there, yeah. And a subject matter expert is aiming for 90% plus.
Okay, when the first LLMs came out, they were nowhere near that expert level. But the strategic focus seems to be on hitting that 60% threshold, which represents the model becoming a kind of competent generalist.
That's the key mark. That 60% score basically means the model can reliably handle most high school or introductory university-level reasoning tasks across a whole range of fields.
And the speed at which smaller models have broken that 60% barrier is, well, it's genuinely shocking. It really defines the current competitive landscape.
Look at the timeline for that 60% milestone, February 2023. The smallest model to reliably hit 60% was Llama 165B. 65 billion parameters, a very large model, needed significant infrastructure.
Okay, Feb 23.
Just 7 months later, by September 2023, Mistral 7B 7 billion parameters reached that same level of general competence.
Whoa, that's nearly a 10x reduction in size for the same baseline capability in just over half a year.
It's incredible progress. And here's where it gets really interesting for the future of efficiency. By March 2024, The Qin 1.5 mixture of experts model surpassed 60% while only using less than 3 billion active parameters during any given moment of inference.
Less than 3 billion active parameters, so the total parameter count is higher, but what's actually doing the work is tiny.
Exactly. Thanks to the MOE architecture, which we'll definitely detail later, the actual computational footprint is minuscule, but it still maintains that generalist capability.
Okay, this rapid compression of competence. It means the strategic need for those absolutely massive, generalized models is rapidly shrinking. It seems like it's only for the most highly specific, super high-end applications now, the really complex edge cases needing maximum nuance.
That's the trend. For almost everything else, the vast majority of tasks, you can now achieve general competence with a lean, mean, efficient machine, and that changes the strategic purchasing decision entirely.
Right, that undeniable trend towards efficiency, it leads us naturally into the next critical strategic idea,
Hmm.
moving beyond that simple choice of either to a more dynamic and.
Yeah, we're talking about the ensemble strategy, the deliberate combination of multiple AI models, maybe old and new, dynamically employed to get the maximum business value from your data.
Because the historic internal discussion was always kind of polarized, wasn't it? Use traditional AI or use an LLM.
Exactly. But the new paradigm, the one based on maximizing value and minimizing cost, it says you really have to use both. And you have to use them intelligently, often within the same workflow.
And the overarching goal is pretty simple then. Achieve the most accurate prognosis or answer or result in the shortest possible time, every time, without paying for compute power you don't actually need in that moment.
Precisely. And to build this kind of dynamic system, you need a strategic tool portfolio. We can categorize these tools based on their fundamental attributes, how they handle data, their speed, their energy efficiency.
Okay, so first up you have traditional AI. This covers standard machine learning, ML, deep learning models.
Your classic stuff.
Yeah. They excel at structured data, they're typically rule-based, and they give you a clear confidence rating. Their core strategic strengths are being small, having extremely low latency, sometimes like single-digit milliseconds, and great energy efficiency.
Mm-hmm. They're still the workhorses for things like high-speed fraud detection, anti-money laundering compliance checks, or, rapid medical image analysis.
Okay, then we break down the large language models, LLMs, into functional types for deployment. First is the encoder model type 1.
Right. This is an LLM that's specifically used for analyzing structured data. It gives you prognosis and confidence ratings, just like traditional AI, but it uses those complex transformer techniques to get increased analytical accuracy. It's especially good at finding complex, non-obvious patterns.
But the trade-off.
The key trade-off is higher energy consumption and increased latency compared to traditional ML. You strategically use these when the accuracy boost really trumps the speed of the traditional AI, when you need that extra certainty.
Got it. The next LLM category is encoder model type 2.
This one has a single, really vital job: converting unstructured data, think like a doctor's handwritten notes or a customer's free text feedback form, maybe a long legal clause, into clean, structured data.
Okay.
Data that can then be processed by other, faster models downstream. It's the necessary bridge between a messy human-generated text and machine-readable data streams.
And finally, the decoder models.
These are your classic generative tools, the chatbots, the code generators. Their main function is just to create new content based on a prompt. So understanding these three functional types of LLM plus traditional AI, that's really the foundation for building these dynamic workflows.
I appreciate the categorization, but let me push back a bit here.
Yeah.
Managing and maintaining 4 different model types. That sounds like it requires different training schedules, different data pipelines, different hardware maybe. It sounds like an enormous operational headache. Why is the potential cost saving worth the complexity of adding this management layer?
That's absolutely the right question to ask. And yes, there is complexity. It's typically managed by a centralized orchestration layer, some kind of smart routing system. But the cost saving you get from not running the most expensive model all the time often makes the investment in that orchestration infrastructure pretty negligible in comparison.
Okay.
This dynamic selection strategy lets an organization run multiple models, switching between them based on the specific situation, the confidence score, the business priorities. You only pay for the expensive, high-accuracy compute when the confidence rating really demands it.
Okay, let's make this concrete. Let's use the source's primary real-world application: dynamic selection and high-speed fraud analysis. like a credit card transaction. You need speed, obviously, customers waiting, but absolute accuracy is crucial to prevent financial loss.
Right. So in this hybrid workflow, when the transaction is initiated, the system's first point of contact is the fastest, lowest cost model available, a traditional AI model. It runs first, instantly generates a preliminary prognosis, fraud, not fraud, and a confidence rating. This execution is so fast, it's often basically concurrent with the network handshake, almost instantaneous.
Then the system makes a calculated strategic decision based on that confidence. So case A, high confidence. If the traditional AI model comes back with, say, 99.5% certainty that this is not fraud,
Transaction completes instantly.
right, you maintain speed, you ensure sustainability using minimal compute. That's the default efficient path.
hmm But case B, low confidence. If the traditional AI model is unsure, maybe the confidence rating is too low, like 65%, not fraud, then the system dynamically switches. It reroutes the request to the high accuracy LLM, the encoder type 1.
And that model takes longer, costs significantly more compute, maybe 50, 100 times more, but it delivers the precision needed for those complex, ambiguous cases where the financial risk is highest.
Exactly.
That is incredibly elegant because you're ensuring that operational efficiency remains the default state for, what, 95% plus of transactions, while still achieving maximum accuracy when the risk truly warrants spending more. You're kind of monetizing the traditional model's speed to save money on the LLM's cost.
Perfectly put. And a second powerful application is handling mixed data sources. Think insurance claims analysis.
Okay, yeah, that data is messy.
Right. It's structured, dollar amount, name, location, but also highly unstructured. The free text description of the incident, often full of slang, typos, specialized jargon.
So the workflow starts with that efficiency bridge, an LL encoder type 2.
Yep. Its single job is to read that messy, unstructured description, the car slid on the ice on the A5, causing fender damage, and convert it into clean, structured data points, like weather conditions, NICE, precise location, A5, impact severity, minor fender damage.
Okay, structured now.
Once that data is enriched and structured, the hybrid approach kicks in again for efficiency. Call it variant 2. That newly structured data is first analyzed by a fast, traditional KI model.
For a rapid, low-cost prognosis and confidence rating.
And the escalation only happens if the risk looks high. Only if that confidence rating falls below a certain threshold, meaning the traditional model is too unsure to make a low-risk call, then the system escalates the job to the slower, high-accuracy LLM encoder type 1 for a detailed, nuanced review of the claim's validity.
Okay, so if we connect this back to the bigger picture, this dynamic switching lets organizations only pay the heavy computational costs of the larger, slower model when the situation truly demands its superior analytical power.
Exactly. This is the definition of maximizing value from your entire AI portfolio. It's about intelligent, cost-sensitive deployment, not just, chancing the largest parameter count available on the market.
All right, we've established the strategy. Hybridize and optimize. Now we need to look under the hood at the cutting-edge architectural decisions that are actually enabling this phenomenal efficiency and complexity management. We're diving into two distinct but often confused concepts, AI agents and mixture of experts,
Yes.
or MOE.
Yeah, and the foundational difference here is absolutely crucial. It's something decision makers really need to grasp strategically. We are distinguishing between task routing and token routing.
Okay, task versus token routing.
Right. While both architectures use experts, they operate on fundamentally different levels within the whole system stack.
Let's define them by their operational level then.
Yeah.
AI agents operate on the application level, right? Sometimes called the macro level.
Right.
They're responsible for task routing.
Determining the sequence of logical steps, figuring out which tools are required, managing the communication between different components, all to solve a complex multi-step problem.
Okay. And conversely, the mixture of experts, MOE, operates on the architecture level, the micro level. MOE lives inside a single neural network model, usually an LLM, and is responsible for token routing.
Token routing. Deciding which specific internal parameter slices, or experts, get activated to process a tiny specific chunk of input text, like a word or even part of a word.
Okay, let's focus on the multi-agent workflow first. This seems like the most outwardly visible architecture. It's a system that gets a complex input and processes it through a chain of specialized agents, right? Designed to autonomously achieve a goal with minimal human input, like setting up a miniature specialized team of AI specialists for a task.
Exactly. The structure is modular. You usually start with a planner agent at the top. It takes the user's complex request, breaks it down into actionable subgoals, and then distributes the work. Then you have specialized agents. Maybe a database agent that's good at SQL queries, an analysis agent for business intelligence tasks, or even a threat intelligence agent specific to security data feeds.
And the workflow isn't just linear, it's a continuous loop, kind of modeled after human cognition.
Yeah, sort of. The agents first perceive their environment, the alert, the document, the user query. Then they consult memory, both working memory for current context and maybe long-term memory for accumulated knowledge or past actions. Then they reason act. They make decisions and use external tools, maybe call an API, run some code, query a database. And finally, they observe the results of their actions before potentially looping back, communicating with other agents as needed to refine the plan.
So the agents communicate and use external tools to reach a complex, multifaceted objective.
That's the core idea. Now contrast that whole operational structure with the mixture of experts, MOE architecture. This is not an external workflow. It's a fundamental design innovation inside the neural network. The model's core weight structure is literally split into specialized internal components, these internal experts.
And the key concept here, the one driving all that strategic efficiency we talked about earlier, is sparsity. That's the main performance advantage.
Absolutely. Sparsity is key. When an input token arrives, like a single word or character, only the parameters of the active experts contribute to the computation. The vast majority of the model's parameters stayed dormant, untouched, uncalculated.
Okay, so how does that mechanism work in detail, the component flow inside the MOE model?
Right, it's usually by three main parts. Input tokens arrive and are immediately directed by a router, often called the gating network. This router is itself a small, specialized neural network. Its whole job is to decide which specialized experts, maybe it picks, say, 2 to 8 out of a total pool of 64 or 128 experts, should handle that specific piece of data.
And it makes that decision instantly based on the token's content. So like a syntax expert might get chosen for certain parts of a sentence, while a factual recall expert gets chosen for a name or a date.
Exactly, that kind of specialization. And those selected experts then process the data in parallel across the available GPUs.
Okay, then what?
Then the merge component takes over. This is critical. It mathematically combines the output tensors, the results, from just those selected active experts back into a single cohesive data stream for the next layer of the network.
Ah, okay. And because only a small fraction of the total parameters, just the active experts, were involved in the heavy lifting, the matrix multiplication.
The inference time and the compute energy are drastically reduced.
This is exactly where that dramatic efficiency we saw earlier comes from. Let's revisit the IBM Granite 4.0 tiny preview model example. It has, 64 experts and about 7 billion total parameters.
Yep. But because of this MOE architecture, during inference, when it's actually running in production, only about 1 billion parameters are active at any given moment.
That's a massive 7x reduction in the active compute footprint, which allows these models to run on a single modest GPU, making them perfect for cost-sensitive enterprise deployment.
Exactly. And crucially, these MOE experts are not like separate AI agents. They don't talk to each other, they don't use external tools, they don't reason about goals.
Right.
They are specialized parameter sets within a single unified model, just trained to efficiently handle different types of input data, syntax, facts, different languages, whatever, for maximum speed and minimum compute.
Okay, the true strategic advantage, though, as the sources suggest, is the synergistic application combining the agent workflow, task routing at the macro level, with the MOE architecture, token routing at the micro level. Let's go back to that scenario of an enterprise incident response system.
Okay. Imagine a security analyst gets a cryptic alert bundle from some system monitoring thousands of endpoints. They ask the system in natural language, is this lateral movement activity? And if so, what immediate steps should I take to contain the risk?
Right. The agent workflow handles this on the macro level, the task routing. The planner agent breaks the complex question down, assigns subtasks to specialized agents, maybe a log triage agent to parse all the raw, messy telemetry data, and a threat intel agent to cross-reference any indicators against known external threats.
Okay, now here is the synergy down at the micro level. The log triage agent itself is implemented as an LLM, and that specific LLM utilizes an MoE architecture.
Ah, I see.
So as the tokens, the raw log entries, the IP addresses, the command line outputs, as they arrive at the log triage agent, its internal gating network, the router, instantly decides which handful of its, say, 64 internal experts are best suited for that specific micro batch of text.
It's making thousands of these tiny routing decisions every second.
Exactly. And the vast majority of the log triage agents, maybe 7 billion total parameters, remain inactive, just sitting there ensuring energy efficiency. Only the select experts, perhaps the one specialized in network protocol syntax or specific operating system logs, are activated for that micro batch.
So the log triage agent processes vast amounts of complex data really efficiently.
And the overall agent system uses that result, combined with the threat intel agent's findings, to deliver the final containment plan to the analyst.
The outcome is pretty profound then. The system achieves sophisticated, specialized, multi-step reasoning through the agent workflow, but it executes that reasoning with the extreme inference efficiency delivered by the MoE architecture inside one of its key agents.
That combination is how modern AI is starting to maximize capability while maintaining an optimized cost structure. It's solving for both complexity and economy simultaneously.
Okay, we've covered the fundamental why, the strategy, and the deep technical how, the architecture. Now we get to the where do I even start? The developer guides we looked at are very clear on the strategic starting point. You must define the specific problem, the latency requirement, the target compute budget, before you even look at a single benchmark score.
Absolutely critical first step, and this immediately frames that core deployment dilemma for decision makers. Do you commit to a commercial SaaS model, like from OpenAI, Anthropic, Google, which offer speed, ease of integration, rapid prototyping?
Right, the easy path sometimes.
Or do you commit to open source models like Llama, Mistral, Qwen, which offer full control, deep customization possibilities, better cost effectiveness in many cases, and long-term flexibility, no vendor lock-in?
Yeah, different trade-offs. But regardless of that choice, the selection process has to be ruthlessly evaluated against those three core factors: performance, the quality of the output, speed, latency and throughput, and price, the operational cost.
For most massive repetitive enterprise tasks, you probably don't need a PhD level model that costs 10 cents per thousand tokens. You need the optimal balance of those three factors for your specific use case.
So how do you navigate this overwhelming market? Decision makers rely on specific tools for market analysis and capability assessment. The first source cited is artificial analysis.
Right. That platform provides the initial high-level overview of the entire model landscape, proprietary and open source. It helps confirm that baseline strategic trend we discussed. Higher intelligence usually means higher cost. Smaller size generally means higher speed and lower price. It helps you quickly map where a model falls on that cost-performance curve.
But as we know, benchmarks can sometimes be, well, gamed or reverse engineered. And that's why the second tool mentioned is so vital. Chatbot Arena from UC Berkeley and LMSYS.
Yeah, the arena is fascinating. It aggregates over 1 million blind user votes. People call it the model's vibe score, or subjective quality score.
A vibe score, seriously.
Well, yeah, but it's invaluable because it captures real-world logical ability, writing quality, coherence, overall usefulness as perceived by actual humans doing complex, non-structured tasks.
Okay, so it often gives a truer, maybe more robust picture of a model's general competence than just synthetic benchmark numbers.
Often, yes. For example, it lets you directly compare how two models, say Granite 8B versus Llama 8B handle, being asked to create a structured JSON customer response based on some complex, messy prompt, its performance in the wild, judged by humans.
Got it. And for organizations committed to customization, data privacy, and having that full control, the Open LLM leaderboard is the indispensable resource.
Absolutely. It focuses exclusively on open source foundation models and all the fine-tuned versions people build on top of them. And crucially, it allows highly specific technical filtering based on real implementation needs.
Like what kind of filtering?
You can filter models based on critical criteria that really impact deployment. Does it run efficiently on my specific GPU architecture? Can it perform local on-premise execution for our sensitive data? Does it meet the real-time inference requirements for an edge device with limited power?
Okay, so that's the essential step for moving from just theoretical competence on a leaderboard to practical production deployment.
Exactly. And once you've narrowed down your choices using these tools, you need to test locally before committing serious capital or engineering time. The sources highlight Llama as the open source developer tool of choice for this initial testing phase.
Llama. Okay.
Yeah, it's a really easy to use utility, lets you download and run optimized, often quantized models, meaning they're compressed for efficiency right there on your standard developer laptop or workstation.
So it's the perfect sandbox for quick iteration.
Yeah.
And security testing too, presumably.
Precisely. You can download a model like, say, Granite 3.1, run a quick functionality check, maybe ask it to translate this legal document into plain English, verify the basic capability, and immediately start experimenting with your own proprietary data in a secure local environment. No data leaves your machine.
And that leads directly to the first major application supported by these local tools, Retrieval Augmented Generation, or RJAG, often implemented using interfaces like OpenWebUI. RA is that critical technique for grounding the LLM with your own specific data it wasn't originally trained on.
Yeah, RAG is essential for enterprise use. The workflow is really powerful. You feed your custom documents, internal corporate policies, engineering schematics, past project reports into an embedding model and a vector database.
Okay.
Then, when a user asks a question related to that data, the vector database rapidly retrieves just the small, relevant context snippets from your documents. The LLM then generates the answer based only on that retrieved context. And, crucially, it provides citations back to the original source document.
Those citations are the strategic payoff, aren't they?
Yeah.
They ensure the source of truth. They help prevent the model from confidently hallucinating information, which is a major risk.
Huge advantage for internal applications where auditability and factual accuracy are absolutely required. You're basically turning the LLM into a highly verifiable knowledge engine focused specifically on your institution's memory.
Right. And the second essential application for local models mentioned is coding assistance, using open source extensions like Continue. This is an extension for IDEs like VS Code or IntelliJ that you configure to use your local Llama model.
That's right. So instead of sending potentially sensitive source code to a proprietary cloud service for coding help,
Which many companies won't allow.
exactly, your developer can chat securely with their own code base locally. They can ask the model to explain the logic of entire files or request complex multi-line code changes like add java.comments comments describing this entire service layer.
And the model generates the documentation or the code right there, in line in the project, entirely within the local firewall.
But the key element, again, is control. The developer always maintains final approval over any changes suggested by the AI. It's a powerful augmentation of their intelligence, leveraging the speed and security of a locally running, highly efficient model. It lets development teams adopt these powerful tools without compromising data security or incurring massive cloud costs. Hashtag outro.
You know, this raises an important question as we wrap up. We've spent a lot of time defining how to build this intelligent, cost-effective ecosystem. We've established that the value isn't really in model size alone anymore, but in the intelligent deployment of a specialized team, both externally via agents and internally via MOE.
Yeah, we've definitely moved from thinking about monoliths to thinking about specialized teams, haven't we? Both in how we orchestrate different models, agents, and how models themselves are built internally, MOE.
So what does this all mean for the strategic decision maker, the person actually building the next generation of applications? The strategic takeaway seems incredibly clear. Efficiency is rapidly converging with generalized competence. You don't necessarily need a PhD-level massive model for every single task anymore. You need the right tool, dynamically applied in an orchestrated way that minimizes cost and latency.
The ability to dynamically switch between, say, a traditional fast ML model for speed and a higher accuracy LLM only for the difficult cases, combined with the architectural efficiency offered by things like MOE, it means we can build systems that are both highly capable and sustainable. It fundamentally alters the economics of deploying AI.
Right. The focus really has to shift now entirely to that orchestration layer, doesn't it? How do you manage this dynamic switching intelligently?
It does. But, and this is the provocative thought to leave people with, the integration of these complex specialized architectures introduces significant complexity and verification.
Ah, okay. How so?
Well, as systems become these ensembles of dynamically switching components, the agent is choosing which external tool or data source to use moment by moment, and the MOE within that agent is instantaneously choosing which internal parameter expert to activate based on the token it sees. The decision-making chain becomes exponentially more opaque.
Right. It's harder to trace exactly why a certain output was generated when the path taken through the system is constantly changing and involves all these micro decisions.
Exactly. So that really is the next frontier for decision makers to explore. How do we build robust frameworks capable of verifying outcomes and maintaining auditability, maintaining that source of truth when the AI is constantly choosing the most efficient yet potentially least transparent path across a vast, complex, dynamic architecture? That's the challenge ahead.